Okay, so in this little lecture we will first talk about controllable decomposition. So, okay, why do we need to do this? So, in the previous lecture we saw basics about controllability, that the system is controllable if the rank of a certain matrix is n, and if that rank is n, then I could actually do something called the pole placement to solve control problems in the state space. Okay, so now we did not answer the question, what if the system is not completely controllable? What if the rank is not n, but it is some number m which is less than n? Okay, so let us quickly check what we can do with those kind of systems. Okay, so let us say that I start with a system x dot is Ax plus Bu, and suppose that the rank of this matrix B, AB A n minus 1 B is some number m which is less than n. Okay, to keep it simple, let us do it with the help of a little example, where A is 0 minus 1, 1, 1 minus 2, 1, 0, 1 and a minus 1. B is 1, 1, 1, a 0, a 1 and a 2. Okay. So, the controllability matrix C, which I call it, is B will just be 1, 1, 1, 0, 1, 2, A times B would be 0, 0, 0, 1, 0, minus 1, and A square B would be 0, minus 1, 0, 0, 0 and a 1. Okay. And we can easily check here that the rank is 2. Okay. Now, what do we do when the rank is 2? I cannot completely control the system, because what I learnt, okay, even though we did not do the proof, is that to place all the poles we need the system to be completely controllable. Okay. So, let us do a bit of a magic here. Let us say I want to transform the system into something else, right, and we knew that so that P inverse AP is a good transform which transform the system from some x coordinates to certain z coordinates. Okay. So, let us construct this P in a nice way now. Let us say P is, I take two independent columns from this controllability matrix. So, the obvious ones are directly from the B matrix. Now, can I add another column here such that the rank of this P is 3, right. So, I am giving you two independent vectors in R3, and I am asking you to construct something else which is again independent of the first two, right. A simple choice would be something like this. Okay. Now, this is an invertible matrix, this P. So, I can always do this transformation. So, what will the new A tilde be? A tilde computed as P inverse AP would turn out to be something like this: 0, 1, 1, 0, minus 1, 0, a 0, a 0 and a minus 2. And what is B? B tilde is 0, sorry, 1, 0, 0, 1, 0, 0. Okay. So, okay, let us carefully look at this. Okay. So, let us say if I write the system like this, right, x1 dot is u and x2 dot is minus x2. It can be easily checked that this this system is not completely controllable, this system, which because you can see there is no direct control which is entering the x2 coordinate. Okay. So, here I can clearly see which of the two states is not controllable. I can easily say that x1 is controllable and x2 is not. Okay. Now, what happens when I do a transformation like this? If I look at this thing here, if I say I have this new coordinates z1 dot, z2 dot, z3 dot is this new 8 times z times u, that z3 has no influence of the control because the entries of the B are 0, whereas z1 and z2 are actually controllable because there is some numbers coming in here. So, what I have done with this transformation is I have split the system into a controllable part and an uncontrollable part. So, this is my controllable part and this thing is my uncontrollable part. Okay. So, what did we do here? What was given to us was a system which was not completely controllable in such a way that the rank of this controllability matrix was some number m. So, based on this m, we pulled out m independent vectors from the controllability matrix. I add remaining n minus m vectors such that the rank becomes n, and I do this kind of similarity transformation. So, while doing this, I have a system where I can clearly see which part is controllable and which part is uncontrollable, and this is what is referred to as the controllable decomposition. Okay. So, there exists a similarity transformation we exactly saw. Okay, I called it P there, but it is T here, it does not really matter. So, that T inverse AT is something like this. So, you have the controllable part, you have the uncontrollable part, right, and even the B splits very nicely into the controllable and uncontrollable part. C will have some numbers, this is not really important. Okay. Okay. So, what is interesting here, right? So, I have a system now which is explicitly written in terms of xc, which is the controllable states, xu, which are the uncontrollable states. Okay. What happens to the transfer function of this? Well, I can simply write down the formula for the state space to the transfer function form C Si minus A inverse B plus D. Okay. So, I will skip these computations, but what is interesting to see is that the transfer function will have numbers or the entries which are only corresponding to the controllable part. AC is the one which is corresponding to the controllable part, BC is also the controllable part, CC is also the controllable part. So, what is important here is that the transfer function is only the transfer function of the controllable part. Therefore, whenever I give you any transfer function, I could do anything with that transfer function if and only if I know that this is a transfer function of a completely controllable system. Otherwise, you see that some poles of the system go missing, or there is some kind of inherent pole 0 cancellation whenever the system is not completely controllable. Okay. So, what can we do with this kind of systems, right? So, say I will just take the other example, which had x1 dot, x2 dot is say 0 0, this is say 0 or minus 1, x1 x2 plus 1 0 times u, okay, which can be written again as x1 dot is u, x2 dot is minus x2. Okay, what can I do with this system? Well, you can see that I can actually control the first state provided that the second state is stable. What does it mean when I say this? Take instead a system which is like this, 0 0 0 1, x1 x2, 0 1 and u, which means it is the same system x1 dot x1 dot is u, x2 dot is plus x2, and let us see how the uncontrollable part of the system behaves here and here. The uncontrollable part here is actually stable, because I can just directly solve for x 2 dot is minus x 2. This is unstable. So, this is bad news, right. So, I can do anything, or I can, there is some hope when the system is not completely controllable, if and only if the uncontrollable part is stable by itself. Here I could do nothing with the system, because whatever smart kind of input I choose, whatever expensive, whatever the best kind of view, my x 2 is still unstable, which means that the overall system is unstable. So, there is nothing I could do with this kind of systems, right, and therefore, we have now a weaker notion of controllability, that is stabilizability. For the system A B, if the uncontrollable modes are stable, then the system is said to be stabilizable. I can do something with the system only if the uncontrollable modes are stable. Okay. And then as a very small extension to the definition of controllability. So far we have talked about the state going from point A to point B in some finite amount of time, and we just relaxing that the point B is actually the origin. Okay. So, what do I say? Well, I want the output to be controllable, not the states, because typically I have x 1 dot is a x plus b u, y is some c x, sometimes some d time u. So, the definition translates, can I transfer the output with some initial value y at t naught to some value y at t 1 in finite time and with application of some control. This again I will just leave for you to derive that the corresponding rank condition would just be in terms of the output matrix also. CB, CAB, CAN minus 1 B times D should be P, and this P is like the number of outputs here. Okay. So, what have we learned here is, what do we do if the system is not completely controllable? If the system is completely controllable, I can just use u equal to minus kx to achieve the desired performance in terms of placing the poles at the appropriate locations. Even in root locus, what we were doing, we are just shifting the poles, right, via the root locus, shifting the dominant poles to the left depending on if you wanted a faster response, right, and also poles corresponding to when we were doing the lag compensation, right. So, we are essentially playing around with the poles. This also is something similar. Okay. So, what do we assume when we say u equal to minus kx? We always assume that x is measurable, that somebody is actually giving me x. Sometimes, now what am I measuring here? I am measuring the outputs y equal to c times x. Let us just ignore d for the moment, right. So, x, so given the measurements y, when can I get all of x? This is possible if and only if the output matrix C is invertible, okay, which means that the number of states and the number of outputs are the same, or this matrix C should be invertible. But this is not possible all the time, because sometimes we will have maybe only 5 outputs measured when the complete total number of states is 10. Okay. So, in that case what do? Is there again some hope? So, can we use the input, we know the u all the time, and the output measurements over a time interval to reconstruct the states, reconstruct x naught for example. So, this is what leads to the definition of observability. I will not go into the details of this, but we will just understand what it means. So, I will just stop by just giving a definition and how to check the conditions of on observability. Okay. So, what is the definition? The definition says that the system is observable at time t0 if this x t naught can be determined by the observation of the outputs over the time interval t naught to t1. Okay. Again, these are important because all states may not be measurable. So, a simple computation like earlier would suggest that a system is completely observable if and only if the rank of this observability matrix is n. Okay. So, I have dimension np cross n matrix, which is this one. This is called the observability matrix. So, again given the properties of the system which essentially come from C and A, we can determine if the system is completely observable or not. And also note that the matrix B does not really play any important role in this. Okay. So, this is where we will end. We will try to post some problems related to the various concepts which we have derived in state space analysis, and also possibly related to the observer or the observability matrix. And this is actually, this covers a good amount of stuff related to the state space analysis. And I will not go deeper into how to design observers and so on, or how to design observers and controllers simultaneously for a system. That we will leave for some advanced course in control. But for the moment, this is all what I thought would be useful to you, to give you some insights on the theory on state space. So, this is the last lecture of the entire course, and I hope you enjoyed the course and you had a good time. We actually had a good time preparing the course content, interacting with you while we were doing through the discussion forums. And well, good luck for your final exam if you are taking those, and thanks very much.